So we will go now over what we learned so far from this simulated cadences and math analysis relative to questions posed in COSEP. Again, that stands for Community Observing Strategy Evaluation Paper, where you can find science-driven thinking for cadence optimization as of about 2 years ago. That was a large project by science collaborations led by Phil Marshall, and there we posed some questions that Lynn will discuss in next few minutes. And then we will go over of the other 10 contributions from you guys. You can see links on our official agenda page for the slides that arrived since yesterday. So we'll go through them, and then we'll have of the order an hour left for open discussion of a few open questions, and it will give a chance to you to ask questions, either technical questions about simulations and analysis from Peter and Lynn, or you can ask SCOC members about details of the process and everything else. So let us start with Lynn first. Lynn, it's all yours.
Thank you. This is the survey strategy progress post COSEP, and it's worth noting that the question was, can we answer any of the questions that were posed in the Community Observing Strategy Evaluation paper? And these are my evaluations based on what we have in the metrics so far, or our evaluations. And it's not, the reason I emphasize these are, our group's answers is because this is not the opinion of the SCOC. I can't speak for them on this front yet. I would say that this is what the metrics show us, and so these are what we think are the answers. There was, like I said, we had those questions in the COSEP. There's the link up there. We have more simulations now to investigate the questions, including families which vary the parameters over a range which matches the parameter space. And we have a set of core science metrics. So yes, we probably can answer these questions. The first question was about the area coverage versus the number of visits, or co-added depth trade-off. So the full question is written out there, but basically the question goes, should we maximize our sky coverage to 30,000 square degrees, for example, or should we have the more limited baseline of 18,000 square degrees? So one of the things we found is we've used a more conservative weather model, which is conservative but still matches reality. So it's just on the conservative side of reality. And then if we take out time for the deep chilling fields and we take out time for reserve, like for terrible breakdowns, terrible weather, it looks like what we could probably cover to the SRD goal number of visits, which is 825 visits per pointing, is about 19,000 square degrees. Probably a little bit more, maybe this is about the right number. So anyway, what we see is that extremely large areas like 30,000 square degrees would require going below that 825 visits per pointing. And so perhaps they're not so practical. Now, the other thing we note is that shifting the wide, fast, deep footprint to low dust extinction areas improves a lot of those cosmology desk static science metrics. But it does require adding more coverage in the galactic plane of bulge, because otherwise you just don't have enough visits there. So that means, like, let's increase the area built beyond that 18,000 square degrees to cover the bulge, and then add more area again for solar system metrics for big objects, because that improves the metrics for finding those big objects, like I mentioned in the talk before. So if we move the wide, fast, deep, 18,000 square degrees, and we add area to other parts of the sky that are targeted for for the galactic science and for solar system science, it improves all of those core science metrics at the slight cost of SRD metrics. So what you see from this is like, hey, maybe we should increase our area to about 19,000 square degrees. Again, this is my opinion. The SCOC are not are still going to be considering this and taking feedback from the community. So I talked a bit about this in the previous talk. This is that same plot with like different core metrics, SRD, the desk static science, the transients and variables, and then the solar system objects on the bottom in this right-hand side. The different kinds of footprints are color-coded with these different kinds of area. Basically, we see what the footprint definition is matters, but also that if we get to a footprint definition that we think we like, we probably are talking about increasing the area to about 19,000 square degrees. So the answer here, yes, I think the answer is increase the area. Take take a wider area with fewer visits per pointing. Then the next question is about rolling cadence and time sampling. Are there trade-offs between uniformity of sampling and frequency of sampling, which actually covers a wider area than rolling cadence, but rolling cadence is like a very good example and one that we've been thinking about a lot. So the idea with rolling cadence is you take a portion of the sky and you cover it more frequently during a short period of time, and then during some period of time, and then for the rest of the time that is not when it's not on, it's then off and it gets a lower frequency of visits. So there's a lot of variation you can make here. You can change the amount of area that's in focus. You can change how long it's in focus. And so we've broken this down to some basic kinds of variations where we do bands of declination, and they can either alternate year on, year off, or maybe they go 1 year on and then 2 years off. I think we've seen that going to more declination bands so that you say have 6 declination bands, and then you spend 1 year where you're doing the field, that portion of the sky very frequently, but then you have like 6 years off, is probably a little bit too fragile to weather. So I think that that's maybe not the best option, but again, this is something we're still looking at. What we see so far is that the supernova discovery metrics show improvement, but these are also being driven by gaps, sampling gaps in the bluer bands, particularly G, around full moon. So probably I think we need some further simulations and analysis of those simulations here. The other metrics we have so far don't show an obvious improvement with rolling cadence. This is an area I think that has a lot of potential for new metrics, particularly sensitive metrics which are sensitive to medium timescale events, which are maybe not highly U-band dependent, and that would be a great place to say, hey, if this is useful or not. So this question I think is pending. The next question is the single visit depth, the exposure time versus the number of visits. So this was another one of the breakouts from the last session, basically. So the question is, does the science case place any constraints on the trade-off between single visit depth and number of visits? Especially this is something to look at in the U-band, where readout noise is making an impact on the U-band visit depth. So what we see from our metrics is fewer U-band visits is very negative for transient science, and the TDE metric, tidal disruption event metric, is very dependent on U-bands. It's kind of an extreme example of this. So if we want to make longer U-band visits, we can't just have fewer of them that are longer. We have to shift visits out of the other bands to counteract this. So we're working on simulations and evaluating simulations like this. Longer visit times in general show a drop in most of the metrics. And this is because of a drop in the number of visits per pointing. We didn't intend to show this with the variable exposure time simulation, but what happened was that the exposure time went to 3.2 seconds. The mean exposure time went to 32.2 seconds instead of 30 seconds. And you see almost every science metric drops a little bit compared to the baseline. So most likely longer visit times are bad for most science due to drop in visits. Shorter visit times, often will result in decreases to science metrics, but this is going to be dependent on the how much shorter you get and whether or not this is how this changes in terms of the completeness for solar system objects and transient variables where they depend on the single visit depths. So I think this is something where we maybe need a few more simulations to look into this. So, okay, so the radar plots, we showed a few of these before. When you have just one or two simulations, they're much easier to see what's going on. You can see that in each of these, the blue dots are from the baseline. The orange dots are from the variation on the baseline. Each of the metrics are normalized to what the value was from the baseline. So 1 is the same as the baseline, more than 1, so further out in the circle is better than baseline, less than 1 further into the circle is worse than the baseline. So you can see on the left is where we did the long U-band visits, the TDEs rather, have the detection of TDEs drops significantly. And on the right is when we have the variable exposure time. And so you can see that a lot of metrics drop when you have this variable exposure time. And the problem is that the visits were slightly longer over the sky, so you have slightly fewer visits. The FONV metric, interestingly, increases. So that's actually saying that per pointing, the median number of visits per pointing is increasing. And the reason for that is because for whatever reason, they ended up being slightly more evenly distributed over the sky. So more visits seem to be better than deeper visits, but U-band still may be a special case, and we need to look a little bit closer at that. Galactic plane coverage. Does the science case place any constraints on the galactic plane coverage? I think that the answer to this question is basically yes. And I think probably without any metrics, this was probably something that people would say. But here, I think to understand exactly what galactic plane coverage we should have, more metrics sensitive to the overall plane coverage through the halo disk and bulge would be useful. Basically, we see that for the metrics that we have so far that are, especially the fast microlensing, which is galactic microlensing, show that increasing the number of visits in the galactic plane improves the science return. So here, this is, again, the footprint simulation. And so you see on the top is the SRG metrics. They drop because we have fewer visits per pointing. But when you have more visits distributed towards the bulge, in particular in these cases, these ones to the right of the plot here, then you do better at the metrics that are related to the bulge. So yes, I think the answer is we should increase coverage in the galactic bulge, but exactly how we should increase that is probably still to be determined. How do you distribute visits between different filters? So this is interesting. We're working on a photo-Z metric that's in progress. Melissa Graham has done a lot of work on this, so thank you. And then that has a lot to say about how we should distribute visits between filters, because photo-Z's all over the sky is very important. The other things we see is more U-band visits is good for transients and supernova 1A. It's bad for solar system science. Solar system objects are not really visible in U-band, but U-band is really useful for characterizing transients. More G-band is kind of good for proper motion and parallax. This is assuming a flat SED, however. More I-band is good for desk static science and galaxy count metrics. And more Z and Y-band is bad for almost all metrics, with the exception of noting that we do not have the photo-Z metric yet. Also worth noting is we don't really have a metric that focuses on very red objects. And that might change that comment that more Z and Y is bad for the metrics that we have now. So here we have the same kind of metrics, the SRD on the top left, transients and variables, plus the supernova 1A metrics on the bottom left, the desk-wide festive static science metrics on the top right, and the solar system on the bottom right. And these are these filter index family of simulations. So we just have the Wi-Fi deep, and we vary the filter distribution across the Wi-Fi deep. I swapped out the names of the filter dist underscore index 1 metric or run simulations with what they did in the bottom labels here, just because it's a little bit easier to see. But you can see that there's a lot of variation, like primarily with U-band, it's either really good or it's really bad. And then I-band is like pretty good for a lot of things, or at least neutral. G-band is kind of good. In general, I think basically what we have currently is likely distributing the unhappiness relatively evenly. We don't have an answer for this especially because we're waiting on the photo Z metric, but we're probably pretty close to where we want to be. The deep drilling field cadence, do we have constraints on the deep drilling field cadence? We had 2 white papers with specific deep drilling field, extragalactic deep drilling field cadences. Sorry, I'll talk about deep drilling fields here in terms of extragalactic deep drilling fields specifically. We have simulations which match those requests, as well as some other ones where we have a daily deep drilling field and the current existing standard. We kind of need more specific to deep drilling field metric, deep drilling field regions metrics. So yes, there are constraints. We got that message from the white papers, but we're still pending the evaluation of our imperfect implementations. And it's worth noting that even when you specify a cadence, in reality, you're not exactly going to get that cadence because of things like the lunar cycle, the filters being swapped in and out of the camera, and weather. So the evaluation of how well this goes is still pending. Pairs in the same filter or mixed filters. This is assuming 2 visits per night. Should we do visits in the same filter or different filters? Obtaining pairs in the same filter is more efficient because the filter change is 2 minutes long. So you get about 4% more visits overall if you just stay in the same filter. Solar system science benefits when pairs are in the same filter because when you detect an object, you're more likely to get 2 detections in the same night, whereas if you split the filters, especially if you split them further in wavelength range, you're less likely to be able to detect the same object. Transients and variables benefit when pairs are in different filters. And in particular, when, oh, sorry, the word missing in this next one. Transients which depend on obtaining U-band colors in a short period of time suffer dramatically when pairs are in the same filter. Sorry, yeah, missed that. So pairs in different filters is very good for transients and variables compared to same filter. So here you see the radar chart with the blue as the baseline, which is pairs in different filters. So they're adjacent filters. Like R and I, versus pairs that are in the same filter. And you basically see that there's some improvement, a small improvement for pairs in the same filter for solar system, but there's a big decrease in especially the supernova 1A metric when it's in the same filter. So I think this answer is pretty clear that we should probably go with pairs in mixed filters. It's clear from some of the discussion yesterday that we should talk about which filters those are, if you're pairing with adjacent filters or further than adjacent. Special cadence for early science. I think that this is still pending because we're not currently dealing with early science questions. We're really focused much more on what should the overall strategy be for the full 10 years, and then we'll come back and look at, okay, what variations should we make on this for early science? Observing conditions. So the question here was, are there constraints on the sampling of observing conditions, possibly as a function of band? I think this is primarily driven by galaxy shape measurements, which benefit from having good seeing measurements in I-band. We don't have a science-driven metric that includes this explicitly, only through image depth. So interestingly enough, though, all of the metrics we do have generally improve in simulations where we prioritize obtaining at least one image per year with good seeing. So this is a little bit different than saying, hey, it's good seeing, observe an eye. It's just saying across the sky, if there's a good seeing, if you have not had a good seeing image yet, take a good seeing image. And that's per year, so it means in each year, you are more likely to have a good seeing visit. The DCR measurements may improve with high air mass visits, so that's a constraint on the air mass distribution. These high air mass visits kind of conflict with other science goals. It's not like necessarily because you have high, with high air mass, you have worse limiting magnitude. So we need a metric to evaluate the value of the DCR driven visits specifically. Otherwise, basically what we see is that adding high air mass visits on purpose brings down our other metrics. So here on the left, we have the baseline, and then the other simulations that I've included there are the different versions of good seeing. So we did, try and get a good seeing image each year in I band. Okay, do it in G and I. Okay, do it in G and Z. Do it in GR and I, or GR and I and Z. What's interesting is that you see that it's a little bit hard to see, but what it does look like is basically every time you include good seeing images in a particular band, things improve. The only one that shows a decrease is the TDE metric when you have G and I, but when you have GR and I or GRIZE, then it increases again. So there may have been something just a little bit noisy about that simulation. But generally what we see is like, once you say, hey, at every point in the sky, I would like to get a good seeing image each year, things improve. And then, so it's a low impact, but low impact in terms of it doesn't seem to have negative impacts, but it's generally good. So I think this is a good thing to do. We can look further at like, should we actually be steering visits into I-band that might have more of an impact, for example. The other question about on the right is when you add the DCR high air mass visits, and basically what you see is that those high air mass visits are decreasing the individual visit limiting magnitude for enough visits that it's noticeable, because the pink line here is the baseline, and generally things are moving inwards, so they're getting worse. So the next question was about variable exposure time optimization. We kind of talked about this a little bit earlier when I said, what about shorter visit or more visits versus the exposure time. In practice, variable exposure time optimization. So the idea here is that you do real-time exposure time variation so that you get a nearly constant single visit limiting depth. And this is, it's kind of an interesting idea. You don't get visits which are so deep that you can't really, they don't fit into the time series because it's the limiting magnitude is so much deeper. And at the same time, you don't get so many images which are much, much shallower. In practice, this is difficult to do properly because of the fact that we really want to keep those overall number of visits the same, which means we want to keep the mean exposure time about the same. So you have something that you really want to aim at, but it's hard to know exactly what that individual visit depth goal should be because you don't know the future weather. So this might be hard to do in real life. In simulation, obviously you can go through and you can change what your depths are until you get the right mean exposure time. When we did this without like redoing these optimization over and over, what we ended up with was a mean exposure time increase of just 2.2 seconds. So we went from 30 seconds to 32.2 seconds, and the science metrics fell. So it's an interesting question. It's probably worth further investigation. We don't have metrics that explicitly look at the benefit of constant single visit limiting magnitude, like not dropping visits out of your time series, for example. So currently what we see is that most of the variable dependent metrics. So these ones like the supernova, and the TD, and the fast microlensing, and even parallax, which depend on the individual visit depth drop. And again, the inside of the circle in this case is 0.9. So they're not dropping as badly as in some of these examples. So this might be something we still want to look at, but they are dropping. On the right, you see the individual image 5 sigma limiting magnitude, so the depths for each individual image. And the solid lines there are from the variable exposure time. The dotted lines are from the baseline. And so you do see that, yes, using a variable exposure time does tighten up that distribution a lot and leads to a lot of visits having the same 5 sigma depth. So for me, I think this is not promising, but it's not closed. Okay, so I'm going to close by just pointing to some links. You can find the COSEP online. It's on GitHub in the LSST Science Collaborations organization. And all of these questions were posed in section 1.3.2. You can find the fall 2020 report to the SCOC on survey strategy, which is where all of these plots and sort of conclusions came from. It's at PSTN 051 is the LSST sort of document number. And then I think the other important thing is to note that we are really, really encouraging everybody to discuss this on community.lsst.org, and in the survey strategy section in particular. So community is a forum for open and public discussion of all of these questions. And it's a really nice place to be able to post your comments and your questions. We are watching it and trying to answer questions there. It's also a place where you can discuss things with the community. Anybody can go and post on there. And so it's not just necessarily limited to the science collaborations, and it's a nice way to reach the wider astronomical community. So that, yeah.
There was a question on Slack from Colin. What is count observation start MJD?
Doesn't need to be online. That's an offline question. Sorry.
Okay.
So you know what that is though, Colin? It's just me not renaming the metric to number of visits.
Okay, thanks.
Any more questions for Lynn? If not, I propose we continue. We have 10 contributed slides. If it takes 2 minutes, it will be 20 minutes. And usually it takes longer than planned. So let's try to go efficiently through that. But before we go there, I would like to share one photograph with you that is very exciting. Do you see it? You should see the dome.
We see it. We see it.
Oh, excellent. Do you see my cursor? Do you see my arrow?
Yes, we do.
Look at these 2 people here.
Mm-hmm.
Now you see how big the dome is. And it's almost done. The message is LSST and Rubin Observatory will happen soon. Get excited, do your metrics. All right, so now I'll stop sharing this and I will share myself your slides, and let's try to keep it to 2 minutes. If you go much longer than 2 minutes, I will be rude and cut you off. So hang on a moment. Share screen. Where did I put it now? That's not good. So there you go. Hang on a second. Give me a minute. I have too many. Oh, I hate this. Eric, do you have access to the agenda page?
Yes, I can share my slides. Would you
Why don't
prefer
you
that?
share your slides until I figure out what's going on with my...
Okay. Do you see my slide now? It's on a white
We
background.
do. Excellent.
Okay, I will start. Thank you. I'm Eric Feigelson. I'm a core member of the Informatics and Statistics Science Collaboration, and I'm representing the ISSC. Now, we, unlike everyone else in the science collaborations, we don't have any science goals. Simply methodologists here to help everyone make LSST do better science with better statistics and informatics. Okay, so what do we have to say about cadences? Well, it ends up that we actually do have something to say, okay, that's general. And it's a theme that is not widely appreciated. That due to irregular cadences, astronomers have been used to, just accustomed to a very narrow suite of sort of mathematically, I won't call them dubious, but just not very well-founded methods. And here are some of them, which are very familiar. There are hundreds or even thousands of citations to these methods here in the astronomy literature. Okay. But it ends up that, in fact, it's hard to do statistics with them. For example, the false alarm probability for the Loam-Scargill parallelogram has been discussed in all of these papers, showing orders of magnitude range in the false alarm probabilities. Is a very difficult mathematical problem. And only in the last few papers here does it look like there's maybe a good answer. Something to do with the generalized extreme value distribution, by the way, in case you're interested. So, is all of time series so messed up? And the answer is no, not at all. There's a vast bulk. I'm talking, you just can't believe how big it is of methodology that's designed for evenly spaced data, evenly spaced cadences instead of irregular. And here are some examples. These are various statistical tests. This is an entire field called autoregressive modeling. Sequentially modeling goes back to the 1940s. Dynamic time warping is for multivariate, meaning multiband, and it's considered to be the hottest thing for time series classification. If you have densely cadenced, evenly spaced data, we generally don't have. But maybe we can do that for one of the deep drilling fields, or maybe one of the mini surveys. Okay, so the issue is that we recommend that a small fraction of the LSST surveys, the extra surveys, not the wide field depth, be devoted to trying to get close to evenly spaced so that these methodologies can be applied and we can learn from them. We can do better science, and we can also help understand the irregular, the mathematics of the irregular ones. So here are the four recommendations that we and the ISSC have to the SCOC. First, there's literature out there. There's things to do and there's things to read. I personally recommend these two papers here. You might find in Sokolovsky some rather classic metrics that you may not have included yet in your cadence metrics. So just take a look at that paper. And then take a look at Who and Talk, very new. And this is innovative mathematics. Okay, this is quite difficult, quite advanced. It's a Kalman filter state-space representation of multivariate, a damped random walk process. Okay, it's a complicated business, but you can see that this is the kind of innovative research that we need to improve the inferences that we make from, in this case, the wide deep fields. So that's what's nice about this paper, is it's addressing even the very sparse coverage of the wide deep field. Okay. So here's just a suggestion that we add another metric, or sort of three of them that are related, to the cadence metrics that we already have. That is a goal to measure how evenly spaced is it. So if you bin the nighttime data into 15-minute bins, what's the fraction that you have empty bins? Is it 10% empty or 90% empty? And so it's the missing data fraction in an intra-night, intra-season.
Eric, we are approaching 4 minutes, so we should speed up.
Very good. Okay. Then choose one mini survey or DDF or something like that to try to get evenly spaced. Okay, because it will, for that one, the ISSC will analyze it and learn new things and help. And there is one proposal that's pending. It's a one-night full observation of one field, one band, every 30 seconds, 3,000 points for 3,000 observations for 1 million stars and quasars, and that is pending, and it is recommended for commissioning. Thank you very much.
Thank you, Eric. I propose that we
I have to
type
stop.
questions in Slack for presenters of these one-pagers. Once we are done with all the slides, then we will go and answer questions. So if you want to ensure you don't forget it, just type it in Slack. Can you see my screen now?
Yeah.
Okay,
Yes.
good. So next one is Gordon Richards.
Great, thanks, Joko.
Is this better?
So either way is fine. So I just want to advertise a couple of things here. The first is that some groups may be able to turn their OPSIM analysis into formal journal papers, but I wanted to suggest that if you can't, or if that's not really worth it, the research notes of the AAS, the new platform that may be a good vehicle for sharing your work with people. And this is an example of a metric that we are basically putting together as a research note. The idea being, people can get credit for their work, in particular if they don't have funding for LSSC science for that matter. So the second thing is, I don't know if Joko, if you can blow up a little bit. So the specific metric, this is a DCR metric based on some code that Peter originally wrote and that my grad student Wei Zhang Yu has adapted, where we're basically the DCR metric that we're presenting is essentially the error on the slope of the differential chromatic refraction that can be measured. And the units are a little bit wrong here, but basically the DCR specific OPSIMs are maybe something like 40% better than the baseline. So that is the error on the slope is 40% lower. And so that'll be important for object classification and photo Z, particularly for quasars, which I'm showing on the right. And this is just the signal to noise of how well we can measure the change in slope from emission lines moving into and out of bands. And I can explain that offline. And the last thing is just note that we've run this through on all the OPSIMs on the SciServer platform at JHU, and so all the OPSIMs are loaded there as well. And there's some instructions for how to use that platform if anybody is interested in using that instead of or in addition to DataLab. That's all.
Thank you, Gordon. Having difficulties with this. So who do we have next? Did I lose my technical problems here? Okay, that's better. Maybe. No, it's not better. So whoever is next, I lost my window. Can you just share your screen?
Okay, I'll do that, Joko. Do you see my screen now?
Not yet. Now, yes.
I mean,
All right, hi everyone. I want to thank you for welcoming me here in your group. I represent some of Euclid news. So I was talking with Dan Skolnick from the SCOC about what could be a Euclid contribution to the discussion going on in this very interesting meeting. And he mentioned focus about the when. And so this is an update on what we know today on where we are with Euclid. So first, quick reminder of our survey, which is 3 components. We have calibration fields, which you will see when you look at the high resolution version of the PDF, some red diamonds, which are essentially 3 deep spectroscopy fields we have across the sky. Then we have the deep fields, and you've heard of one of them, which is a Euclid deep field south. Those are in green on the map again, you'll see them. And then we have the wide survey, which is 15,000. So the deep is 40 square degrees total, 10 in the north, 10 in the Fornax field, which is a CDFS area, and 20 in the south. And then you have the wide survey, which is meant to be 15,000 square degrees in 6 years. And as you can see here, we have the red outline, which is a compatible sky with our constraint. We have our own metrics and all that. And I just want to signal here that the white papers we pulled in 2018 for Rubin signals interest for an extension up to the plus 30 declination. So it's delight. It's a delight for us to see the 30s here. The interest in the evolution of the footprint. We have we have the luxury of stable conditions in space. So we know once we have the launch date exactly how things will unfold over time, over the 6 years, essentially. And so the map here you see here as this thing shows you the schedule over 6 years. And so we have calibration fields, then we go to some deep fields, which is in the northern field, which we do in the first year. We have a lot of constraints in calibration, and then it lighten up for the next years. But essentially, we fill the schedule with calibrations and the deep field, which is a calibration itself, and then the wide areas is the time left to do the wide survey. As you can see here, for the two deep fields, which will be of interest because they overlap the Rubin fields, are the EDF South and EDF Fornax, and the green and blue and red here. And because they are a bit far off from the south ecliptic pole, they have a limited visibility as we go around the sun on L2. And so they will have a very fixed kind of date. So this opens opportunity for synchronized observations of those fields at the horizon of 2023, which is what I hear now for your schedule. We have fixed integration time because we need stability of the spacecraft, and in all these bands, we have improved in performance now with the as-built spacecraft and instruments. We go about 0.5 magnitude deeper than designed for back in at the time of the definition book. And so that's 26.25 sigma point source. And the deep fields will have 40 times the visit and giving you an extra 2 magnitude. We're on track for launch in 2022 fall. The COVID didn't delay much because people were working in clean rooms. The industry kept working. Essentially, the 3 months delay is related to more administrative aspects. And so we didn't suffer too badly. And so if you look at this program, it's all compatible with what could be happening next, and you'll be hearing soon from us. We are the derived data products for Rubin Euclid, and we have just triggered the creation of a working group that will investigate how the data can be combined together for great outcome. Thank you.
Thank you very much. I think it will be easier if people share their own slides. So the next one is Xiaolong Li. Can you please share your slide?
So the Rubin Observatory have the potential to discover phenomena never seen before, but how can we assure strategy under design will maximize our ability to discover astrophysical novelties? We were encouraged by a comment that Edgar made at the PCW 2019, asking if there were metrics for discovery on unknowns. But if we want to discover unknowns, we cannot simply inject light curves and objects into the opsims. So we look at the time coverage in the same and different filters to see which opsims has power to characterize all time scales, as well as the footprint and the depth of the survey. The metrics and the figure of merit are evaluated as follows. We compare the distribution of time gaps with an ideal distribution, and we use the uniform to measure colors within the night and logarithmic to measure light curve variability in the same feature by the clear divergence. And we measure the medium depths of the images. And we also include the footprint extent for the extra galactic size and multiply the footprint by the stars, number of stars within those fields to get the footprint figure merit for galactic size. And for each piece of metric, we can rank individual opsims and also opsims by families. We then concatenate all three figure merit to create an overall figure merit. Next, we will consider the propel motion, and Fabio will talk about it. Yeah.
Thank you very much.
Yeah.
Note there is one question for you on Slack. Let's move on with Fabio Ragosta.
Yes, Fabio will talk next.
Is Fabio on? Yeah, okay.
Yes, I am. I will talk about the proper motion section of this work on how we can be sure to detect true novelties or anomalies. So to survey the ability of this observation strategy to detect those anomalies, we simulated two kinds of population of object that varies in space and time. We simulated a non-galactic population following the Bellini and et al. 2009, and an unusual population for which we chose a uniform distribution in velocity to be statistically as little informative as possible. Then we measure the fraction of unusual object that could be told apart from the usual population. We also include into the evaluation the ability to detect a non-anomalous structure, the Sagittarius stream with LSST, simulated farther away and in a less dense environment. As we can see from the sky map, the three different opsims seems to act similarly. So one message we can take from this work is that the crucial point is the footprint coverage to increase the probability to detect unusual object. So and with this I stop myself here.
Thank you, Fabio. The next talk is by Rosanne Di Stefano. It's all yours. We cannot hear you. Maybe microphone problem. You are on mute. You have to unmute in the bottom left corner.
There we go. Got it.
Okay, we can hear you now.
Okay, how's that? Great. But now can you see the screen?
Now you have to share again.
Tells me I'm sharing it. So first I'll stop and then I'll share it again. Well, it's sort of end of, oh, I see. It's because it's the end of the slideshow. Let's see if we can go back. I'm sorry this is taking so long. There we are. Actually, I'm making a very simple point compared to the people who have been speaking. In reading the report to the SCOC, one of the things that stood out was that the basic simulations tended to underemphasize the galactic bulge and the galactic plane relative to the rest of the sky. And in talking both with people from the transients group and the Milky Way group, there's a lot of angst about that. Because for these two very important science goals of LSST, we won't really come near to utilizing the potential of the project unless we have observations of both the bulge and the plane that are in some sense comparable to the other all-sky observations that we have. Obviously, there are some differences such as crowding, but we do need to make sure that these are included as essential components of every simulation. So here we have, for example, the galactic bulge. We don't need to resolve every star, but we would like to study the population of variables there, particularly since this is a region of stars near the galactic center that we can only study in our own galaxy. Similarly, we include the region of Sagittarius A star, and any variability from that region would be extremely important for us to see, and we can uniquely see it in our own galaxy. I've included the Magellanic Clouds and M31, both as a proxy for our own galaxy and for a very interesting nearby stellar system. So the point I'd like to make is that in addition to helping to us to achieve our goals in these two areas, what we learn about stars and variable stars is crucial for cosmology, or may turn out to be crucial. For example, to resolve the Hubble tension, would it help us if we knew more about the kind of variable stars that we see in galaxy centers? What are the questions that we'll be able to answer by taking a close look at the only stellar populations we can look at this closely, and to try to use that wisdom to understand what we're seeing in the rest of the universe? So there's really only one take-home message that I have from these slides, and this is a request to the people who are on the SCOC and to the people who are doing the wonderful work of these simulations. And I very much appreciated what Lynn said about this, and also her whole set of presentations, similarly for Peter. But that essentially, simulations that are meant to be used to understand what LSST will observe must include the bulge and the plane on an equal footing with the rest of the sky. We can have lots of discussions about what we mean by equal footing, but I think every simulation must recognize that significant coverage is needed for this local part of the sky. Thank you.
Thank you, Rosanne. We will certainly try to minimize your unhappiness as we go.
That's great, thank you.
The next slide is Rachel Street.
Okay, thanks, Jelka. 1 second while I share my screen. I do notice that it doesn't seem to be linked off the agenda website. I don't know why that would be.
Maybe you need to refresh.
Sorry about that.
I have it.
Ah, okay, great. So, well, I will
the
share
link
that.
I see. Okay, never mind. I'll fix it.
Thank you. Hopefully you can see my screen directly anyway. So I wanted to emphasize that a lot of the different white papers that were proposed for galactic plane science highlighted a number of different ways of going about including the galactic plane without compromising the cadence of the Wide Fast Deep survey, and that these are very important and I believe need further exploration in terms of the operation simulations and how we evaluate the metrics. Specifically, I want to draw attention to the need to combine the wide galactic plane footprint with the cadence and the careful choice of filters, because a lot of different white paper authors emphasize that you don't necessarily need to cover every pointing with every filter, and it could be highly productive to try to optimize that selection. And I'm proposing that TBS, perhaps hopefully in collaboration with the STARS Milky Way and Local Volume Group, could develop 3 alternative different footprints of a limited, medium, and an all-encompassing survey footprint that would give the team more information on those regions of the galactic plane which are most important to the majority of science. And we feel that the science collaborations are in a good place to combine that footprint to emphasize those regions which are most important to us, which could then be evaluated in future OpSIMs. And that we can then develop additional metrics and figures of merit to capture a broader range of galactic science than is necessarily considered by the metrics considered in the report to the SOC so far. We feel there's more work that can be done, for example, with periodic variables, just to name one example. And we also suggest that the science collaborations can provide to the team a kind of traffic light scale for evaluating figures of merit and metrics, in the sense that if a figure of merit produces a value within a certain range, we can say this is the green range. If it gives us a value in this number, we're good. The science is happy, we can do what we want. If it's in the amber range, it's okay, not ideal, but we can live with it. And red range obviously indicates that it's a non-starter, the science is not possible, and that this would be a kind of helpful feedback that the science collaborations can provide alongside the metrics that we submit. And so that's it. Thanks very much.
Thank you, Rachel. I fixed the link, so now it's properly linked to the agenda page.
Thank you.
Next talk is Dan Skolnick.
Great. Okay, so I'm going to share my screen. Oh, oopsies, sorry. Was that okay? So I want to advertise that the draft of the LSST desk metrics paper has been posted on the Slack channel. This was posted just a few hours ago. So this is a draft. We are still kind of in the middle of updating it, but it has our presentation discussion of over 30 math metrics that covers both static science, so like weak lensing, large scale structure, and also a number of transient cases. So the goals of posting now was that we want to work with other collaborations, especially on some metrics that there's overlap with. So a lot of that will be kind of the transient areas. And then the other thing that we want to show is that you make the math metrics, but then kind of as Lynn has shown, interpreting them, visualizing them, and then trying to converge between the different science groups, kind of even within desk is very challenging. So kind of looking to start a discussion of kind of different ways to do these different steps that could be helpful for the SCOC. So if you want to reach out for any collaboration or questions, you could reach out to Michelle Lochner or myself, or also we put the individual authors of the different math metrics in the section, so you could reach out directly to them. So that's all I have. Thanks.
Thank you, Dan. The next slide is Yasaman Hamayuni.
All right. Hi, everyone. My name is Yasaman Homayuni. I'm a PhD student at the University of Connecticut working with Jonathan Trump on measuring quasar accretion disk structure using regression mapping. So the idea that I wanted to share today is sort of emphasize on how we can use continuum lags with LSST observations to build a black hole mass census over cosmic time. So typically to measure black hole masses, beyond the local universe, we use reverberation mapping as a sort of a reliable method to obtain black hole masses. However, time dilation effects increases the observed lag. That means measuring reverberation mapping masses beyond redshift of 3 is pretty much impossible because of the time, the long baseline of observations. So this slide emphasizes the importance of accretion disk lags and how we can use these continuum lags that are technically weakly dependent on redshift to measure disk lags as a function of black hole mass. So if we calibrate this black hole mass estimator, we can form a method that is time independent of redshift and relies only on time domain photometry from LSST observations and would be important to build a mass census across cosmic time. And here I'm just showing two different plots. On the left, these are measurements that are expanded from SDSS RM observations of disk lags. You can see the color pointed are expanding a large number of targets compared to the local disk lag measurements, and how there's a diversity of the lags that are not described by the model. And LSST simulations, just back of the envelope simulations, show that how we can expand the parameter space of these measurements. So if you're interested in this topic, you can reach out and ask questions. Thank you so much.
Thank you, Yasaman. And our last slide is from Will Clarkson.
Okay, let's see. Thank you, Željko. Can everybody see my PDF here? Should be one slide.
Yep.
Okay, good. So I'm going to take my -2 minutes of fame just to advertise quickly some of the work SMWLV is doing to try to get ready for this March 2021 deadline, and to request, if anybody is interested to help with this, to please get in touch. We've formed a task force to do this that you can see listed above. We're really doing two main things at the moment. One of them is to try to start simple with the kind of metrics that we know we can say in a relative sense through the point Željko made today. I thought was quite well taken, that 1% rabbit holes are not as useful as 10% relative scalings. So that's underway, and that'll be on the GitHub under the LSST Science Community Workspace. And to advertise, we are growing a public list of Cadence Notes that we are planning on making sure get done, just because everybody is so busy and pulled in different directions. That's public, and if you have any suggestions for Cadence Notes you want to do, please get in touch or edit that directly. We're looking forward to collaborating with the other science collaborations, particularly TVS and DESC being the obvious ones, but I've thrown a few examples up here of some of the Cadence Notes that we already know we're expecting to write, including addressing, for example, the point that the plane is not just the bulge, although metrics that scale with the number of stars will probably benefit more from coverage towards the bulge. But for some science cases, it matters very much where those stars actually are. So that's all I think I need to say. I encourage anybody who's interested to please get in touch. And if the link in the PDF works, you should be able to see the public list of planned Cadence Notes that we're currently thinking about here. So thanks for your attention.
Thank you, Will. So let us now see if there are questions for our 10 contributors. I don't see anything in Zoom chat, but there was a lively discussion on Slack. Some of the questions I already see answered. We can see excited people, excited about collaboration with other science collaborations. Okay, if the link to any of the slides doesn't work, that's my fault. I'll fix it later, so don't worry about it. Since there are no specific questions as far as I can tell, we can move on to our discussion topics. We had 3 bullets, so we don't have to go in that order. I propose that you type in question you want to ask, or at least few words in Slack channel, so that we have some orderly approach to people discussing things. But the topics that we singled out were open questions and trade-offs for further cadence optimization, basically further discussion of those 7 questions that I presented yesterday that are included in the solicitation for Cadence Notes. Then we would like to hear back from you after your experience yesterday with math on DataLab. How else could we help you to get you up to speed to produce math metrics? For example, would it be better to provide list of documents somewhere, or example notebooks, or would you like to have every 2 weeks or n weeks, an hour or 2 with Lynn and Peter to discuss technical details? What would be the easiest way for you to get going? And then finally, if you have questions about SCOC process, we have the entire SCOC more or less online. So this is good time and good place to bring forward any reservations that you may have about the process, or further suggestions, or you can just tell us this is all so fantastic, we are so exceedingly happy, or you can do any comment that you want. But to keep it orderly, I propose that we just keep adding comments to Slack, and we'll go in that order. Don't be shy. This is your chance to talk to people who will be making recommendation. Slack says several people are typing. Let's see who is the fastest. Question from Rachel. How can the project go about coordinating LSST surveys with those from other projects and missions, such as Roman Space Telescope? That is a very good question. It will include both the project and SCOC and the Science Advisory Council. And I see Michael big on my screen, so I will call on Michael to start first, and we'll go from there. You're on mute, Michael.
Sorry, I had to find the right window. I apologize. As Željko said, this is a discussion that that has been that involves a variety of players. And in addition to all the bodies that Željko just described, it actually ends up involving the funding agencies as well. There have been discussions, for example, for quite some time with the Euclid collaboration, and Jean-Charles gave a sort of a summary of some of the Euclid thinking that's currently going on. But so that is one example. There's been discussions with the Roman Observatory, what previously known as WFIRST, about coordination there. One of the things that I think will be perhaps quite useful is to actually formally define metrics that capture the synergy or overlaps with other facilities. For example, again, from the Euclid point of view, if one can push further north, that becomes very useful for Euclid overlap, and getting a metric that explicitly captures that, I think may be one thing to do. There's a deep drilling fields with Euclid in mind, also with WFIRST in mind, and trying to maximize opportunities there might be a good thing. I phrase this in terms of Euclid and Roman. I'm not we can have a broader discussion about other other facilities out there that with whom we want to have synergy, and that's probably something to discuss via Slack.
Thank you, Michael. I'd like to pick up on that because there was obviously quite a bit about Euclid, because those discussions have been going on for some time, and that's great, and it's obviously very scientifically valuable. But I am a little bit concerned that the focus has been explicitly on Euclid, and that we haven't fully explored potential overlap with Roman is a good example, but no doubt there are others. And that it would be really great to have a high-level process involving all of the major groups involved, and get that going sooner rather than later. I know there is a high-level interest from the Roman mission in doing that, and it's really a question of getting the right people in the room and moving that discussion forward.
Yeah, I'm perhaps not the most up-to-date person on that. There were some rounds of such discussions now several years ago, and there was even a formal white paper is the right word, document posted to AstroPH now several years ago. I'll find the link and put it into Slack, describing this, but it is a little bit dated. And one interesting question, broader question is, are we thinking about static science or variable science? And if the latter, do we need to coordinate in time? So
both, and yes.
The answer is yes.
Yes, it is. And I do know that from the Roman side, I've had some discussions with Julia McHenry, the project scientist, and she has suggested having a workshop about this, including the Rubin team.
Yeah, there were workshops or semi-informal discussions some years ago, but I'm not aware of what's happened more recently. Others may have more recent information than I do.
Yeah, the Roman team reached out to us for a while. They considered their science plan as more or less, I wouldn't say frozen, but steady. And then recently there was renewed effort to revisit everything they planned from the science point of view. And there are a number of committees that were stood up by Roman leadership. And indeed, we have quite a decent Rubin representation there. I am on several committees. And so there is a direct discussion of how we could optimize science together. This is good news. The bad news is that there are some other programs that I'm not aware of direct discussions. Someone asked about Foremost. There was nothing technical as far as I know. There were discussions at the directorship level, but we haven't come to a level of technical detail as we did with Euclid and Roman. And someone also asked about DESI, I think on Slack. Same answer for that. We have not started any deep discussions as we have with Euclid and with Roman. I see Lian, not Lin, but Lian Guy, our project scientist for data management, who is leading a group, a cross-project group with Euclid. Maybe he wants to say a few words about that work. Lian, go ahead.
Hi, thanks, Jelko. Yes, in fact, I'm leading this from the Rubin side, and Jean-Charles, who's on and who just gave us a very nice overview of Euclid, is my co-chair leading it from the Euclid side. So we've just started to put together a working group that's looking at what sort of derived data products we can define and that we could possibly produce between a joint processing between the two surveys. We've really only just got started on this, I'd say.
Thank you, Lian. So to summarize then this point, if you see obvious other projects where we could benefit greatly by better coordination with them, then please do push on that. So far,
how should we do that? Who do we reach out to? How do we push that process forward?
I believe the easiest way would be to exert pressure on Michael Strauss as chair of the Science Advisory Committee and on myself as the project scientist for OSST. And then we will redistribute pressure on other agents.
Okay, thanks very much.
Okay, let me see. The next one was discussed. Canute is raising the question of footprint. And indeed, our team, Lynn and Peter, have produced a proposal to SCOC that we change the footprint that we have now in baseline with what it's called combo dust footprint, which is slightly different. It's not fundamentally different, but it would be better than what we have in baseline. And Peter is already answering this on Slack. Peter or Lynn or anyone on SCOC, would you like to comment further on the question of footprint?
If someone else wants to comment, that's great. I just wanted to say, basically what we're talking about here is a shift of the footprint and then actually increasing the area that gets a large number of visits. And the reason that we would like to do this earlier rather than later in this process is because if we do this is basically we're adding a trade between area and the typical number of visits per pointing, as well as shifting the footprint around somewhat. All of our metrics seem to indicate this would be a good trade, but when we do things like rolling cadence or other work where we're trying to pull more visits out to extend the U-band exposure time, those will all, it's possible that doing those different survey strategy optimizations will behave differently on this different footprint where we're trying to cover more area than they do when we have this older footprint, the traditional footprint with a smaller area that gets a large amount of visits. So I think—
Can you put that up? Do you have that comparison? It might be helpful just to see what the old one looks like and what the new one looks like.
Yeah, give me just a second though. I have the two side by side and the older.
While we're looking for that, let me add a comment. We are not talking here about pulling the rug underneath you and replacing existing simulations with some new set of simulations. We are freezing them as of today, as of this workshop. We are issuing solicitation for Cadence Notes, and what is available today is what your Cadence Notes should be based on. However, in questions like this one, is it going to be combo dust in the next incarnation of baseline? That is related to question 1 in Cadence Notes. And if you have strong opinion about it, then you should please submit Cadence Notes that either tells us do it or don't do it and explain why. What are your arguments? Okay, back to Lynn.
Can we, okay. We should talk a little bit more like about the these runs are all frozen. I do agree, like we want to make sure that the runs we have are the runs that we want people to evaluate and we don't change them unnecessarily. However, there are some extra kinds of simulations that people have asked us for specifically, or that we want to fix some issues with, and in particular, those are the rolling cadence ones. And so I think we can work with people if there's any difficulty with replacing the simulations, but I also don't want to say like, you only have those ones to work with.
We could add simulations. We could perhaps even invoke holiday season and say nothing will be done much until January. But we already have feedback that some people were somewhat unhappy about having multiple versions of simulations. And if we keep going in that direction, it may become unwieldy. So we need to clearly define what is the set of simulations that we will do numerical analysis of.
Yeah, I am totally sensitive to that question. I think it's also a little bit funny. Yeah, and the multiple versions of things is a little bit like driven in part by because we didn't want to change older simulations that people might have. So there's some simulations which were replaced, but like yeah, as Tim Lister pointed out in the Zoom comments, the Twilight NEO simulations are definitely need a lot of work. They need a revamp basically. So I think there are simulations that we've already got the feedback that is not a good simulation and we need to fix it, and here's how you can fix it. And that's part of what the Cadence Notes are for. And I don't think we want to handicap people by saying, hey, no, you can't actually have a simulation that is closer to what you were looking for if they've already said, like, okay, that was not right. Give us something that we can actually evaluate. So I totally agree. We don't want to change things unnecessarily. We definitely also, I think, want to change the things that are clearly not meeting people's needs. So,
Well, I think maybe rephrasing, Lynn, rephrasing things a little bit might be better, right? So it's not like you want to change the baseline. I mean, the baseline's still there. It's just that you want to look at optimizations which are folding off of the new combo dust simulation, because that seems better for a bunch of things. And so it may be that that's the direction we should start optimizing.
Okay.
Right.
Yeah. Well, so here's the other thing that we get pushback about is that we have so many simulations. So when we have so many simulations and then we're saying, actually, we're going to try some of these optimizations from this other footprint as well, then we're multiplying the number of simulations as further. And so I can see that there's points for one way and the other way, you know, for different approaches. For freezing everything now, because then it's easier for people to know what's available. They don't have to redo their work. Or for saying, okay, we're going to fix the simulations that are clearly we didn't do a good job on, and we're going to give you something that's better to evaluate. And then there's also the question of like, okay, if we think that something is better and we would like to see like what happens when you do rolling cadence on the combo dust footprint. Spoiler, it's already a little bit folded into the combo dust simulation, but what happens when we actually explore like multiple ranges of rolling cadence on that simulation, for example? And then you have more and more simulations to evaluate. And so I think like there's a couple of goals, like make the number of simulations smaller or as small as possible. Because the thing is, when you're trying to evaluate these different families, you kind of need a lot of different simulations. We have the goal of like keep the simulations the same as long as possible. But the problem there is that, you know, the pushback on that is that we need to make sure that they're also at least doing what they were really intended to do. So it's just a little bit complicated. I totally appreciate that. Yes, we should keep them the same as much as possible, and we should keep the number of simulations as small as possible. And maybe one way to do that is to say, here's a subset of simulations. If you evaluate nothing else, at least look at these. And then there's just a few of them, and we could keep those the same. And then we can say, okay, if you thought that this was kind of good, but maybe we didn't do a good job, and you are saying, actually, in order to be able to see if this particular survey strategy variation is useful, like the U-band exposure time, we need this other simulation that not just increases the U-band exposure time, but also adds to the number of U-band visits. Then we can add that, and maybe the people that are very interested in that can evaluate that. It gets a little tricky. This is why we want all the metrics to come back to us in the math team as much as possible, so that if we do change the simulations and all of them, we can just rerun everything, follow through the comparisons that we have that are fairly automated, you know, or at least generating the plots is fairly automated, and then we can say, show you these plots and walk through what we think that means, rather than saying, okay, science collaborations, please go and evaluate these all the time.
So there is a question from Siegfried that formally came before questions by Eric Weiser and Razan and Dan on Zoom chat. But given that these other three are related to what you just said, Lynn, let's answer those first, and then I'll go back to Siegfried's question. So Eric asked, would it be possible to freeze the sims at V1.7 In other words, not to have V1.8 until Cadence Notes are in, but to still add improved replacement under quotation marks simulations as V171 during the next couple of months, and then Skolnick gives +1 on this comment. So what do you think? Is that possible?
I think that was actually our goal, was to come out with a replacement for some of the ones that we've actually already worked on and have a replacement in early January, and then in February replace the other ones that we are still in progress figuring out how to update. So I suspect in early January, you'll have the replacement rolling cadence, a cadence driver on the wide fast deep that changes the when we take the blue band observations. So this is to address that question of like, is it the cadence that's suppressing supernova 1A detection, or is it also the rolling cadence? And do you need both? And then these extra exposure, U-band exposure time simulations. And then probably it'll be more like February before we replace the Twilight NEO runs. And maybe we will also look at some seeing variation, different seeing variation runs at that time too. So that's the plan, and that would be V1.7, and then that would be the same until March. That would be it. March is when the Cadence Notes are due.
Thank you, Lynn. It's great to hear you're so optimistic.
I am so optimistic. I was going to say though, one thing about that, because we have not got any sort of consensus on the change of the footprint yet. I don't think we were not planning to do a bunch of extra simulations on the combo dust style footprint. If that is something that people want, we can add that. I think they should be fairly simple to run because a lot of the configuration is very similar, but that is not currently in our plan.
Lynn is very optimistic, but I keep looking at those boxes behind her. And those boxes are there because she is moving the entire household to a different country. And so she will be missing probably until February. And she is 50% of our team. So we have to be careful about what we promise.
Yeah, on the other hand, I will point out, Peter actually already has the new rolling simulations done, and we just have to go through and run all the rest of the metrics and verify things. And changing the U-band exposure time a lot of this stuff is actually relatively simple once we know what we're trying to do. It is usually a little bit more time to verify how the stuff worked the way we wanted it to. But U-band exposure time is pretty straightforward.
I guess that can pass as an answer to Rosanne's question, how difficult is it to get to new simulations, and is that major input of time for the team?
It depends a lot on what's being there.
All right, so I'll go back now to Slack. Siegfried asked, could you please sum up the current SCOC policy towards small satellite constellations such as Starlink? Do simulations have to take related effects losses into account? So short answer is that there is nothing much SCOC can do about it, policy-wise. Longer answer comes in two flavors. So if we talk about policies, there is a lot of effort by AAS, by IAU, trying to come up with regulations that would minimize the impact of Starlink and all other satellite constellations on astronomy worldwide. And we have significant input to this effort via Tony Tyson, who is spending a lot of time and providing lots of energy for these efforts. Recently, there was a paper in AppJ talking about quantitatively about what would be the impact of these satellites on LSST survey. So it turns out that we can, by and large, decouple the two, I mean, impact of Starlink satellites and cadence simulations. As long as we are not going to impact our decision where to point next because of these satellites, we can decouple them. There are some proposals that we should modify where we point, based on predictions where the satellites would be. But preliminary simulations that Peter did show that we would not gain much and probably would even lose on efficiency. Basic problem is that there will be lots of these satellites if they really launch them at the rate that they claim, and they move so fast that it's very hard to take such a big circle as our field of view is and find a place where there will be no track for as long as 30 seconds. Because these little vermins will be zipping around like flies, and it will be very hard to avoid them. Now, on the bright side, you can ask, well, quantitatively, out of all the pixels that we will collect in our images in those 2.5 million visits, or of the other 2 million visits times 3 gigapixel, how many, what fraction will be lost, or not maybe lost, but covered by satellite track. And so Peter did simulations that show that fraction of fields of view, of visits, that will have a satellite track in them, given some assumptions. You can go to that UpJ paper by Tyson et al. And find all the gory details. That fraction varies from 10% to 15%, 50%, depending on time of the night, some assumptions about constellations and so on. Then you can ask, well, given that there is a satellite track in our field of view, what can we do about it? And so then, at the very least, you can find and mask it. And that would, together with the fraction of fields of view with satellites, would come to of the order 1% of all pixels in LSST survey would be masked because they had a satellite trail on them. And then you can ask, well, can I be smarter? And instead of just masking them, can I model them and subtract them out? And now here, the answer depends on what science you want to do. Yes, you could model them. You could then include them in your object detection, and you could recover a number of objects that you would not detect if you just mask it. If you model background as having satellite trail in it, you could recover detections and measurements of objects that fall on the trail to some increased background level. Some other science like weak lensing and correlations on the sky would require more careful treatment. You would have larger mask or better fitting. There are also detailed calculations by Tony's team that show that you have to be more careful and you really need to go further out, more than 1% of pixels, if you want to be dead certain that there are no systematics that could impact cosmological parameter estimation. So it's nuisance at this time. It's 1% of pixels, is not something that will radically change what we want to do. But if they continue putting satellites up there, if we don't mitigate their brightness, if there will be more satellites that we assumed, then it could become significant problem for the survey. At this point, we are decoupling it from cadence simulations. Siegfried, does that answer your question?
Thank you, Joko. It's just fun that now the vermin of the sky is suddenly ArcSats and no longer asteroids. Makes me very, very happy.
That's right. I think it was Alan Sandage who used it first for asteroids. Let's see. We have a question by Bryce Bolin. Will it be possible to visit footprints in the Twilight Survey more than twice per night, like described in the Twilight Survey light paper? Lynn already provided answer. No, she provided more questions. Well, at this point, many things are possible because they are just simulations. But we do have that white paper that I believe we have not yet implemented, but we are planning to, and Peter and Lynn can correct me if I'm wrong or confirm. We do plan to improve twilight observations with solar system in mind, right?
Right, so the new simulations, I think in general in any new simulation, and this is post the 1.6 release, we have started taking twilight exposures in pairs instead of just single exposures. The reason we didn't do that before was because we were looking at the twilight time as changing too rapidly, but we figured a way that we could work with that. So now the twilight visits are just general visits or in pairs. They're not in more than pairs, which was the request from the Twilight NEO survey. The Twilight NEO survey also asked for short exposures. And it may be that that is not, the white paper for the Twilight NEO survey, we implemented basically what was requested. What turns out that we implemented is not actually what perhaps was the best way to do that, what was the way that they actually had in mind. So it's a lot of like question of how you specify something when you're talking to somebody who's not necessarily an expert in your area, and the assumptions that you have that maybe you don't write out explicitly, which is something to take away for everybody, right? It's like, okay, if there's something you think people would assume, like maybe write out what that would be. So that's one reason we need to go back and rework the Twilight NEO survey, mini survey strategy variations we have. I think that the variation, once we redo those, it will reduce the impact on other science, at least to some extent, because we are probably going to have less visits in the Twilight NEO survey, but they will also be more effective for detecting near sun NEOs. So I think that'll be a win all the way around. We should definitely do it. I don't think that currently we're planning to take the rest of the Twilight time and do triples or something of visits, because it's just not long enough. So when you do longer exposures, the short exposures in the Twilight NEO survey, you could do that part of the sky 3 or more times. But if you're doing a regular length exposure, I don't think you cover enough of the sky to do more than just a pair. But I would like to clarify that with Bryce.
Thanks, Lynn. I don't see any other comments on Zoom chat nor on Slack. I would like to have a screenshot of my Zoom screen for our communications team. And there are only a few people with their cameras on. So could you just for a second put your camera on, and whichever first screen I get from Zoom, I'll try to do, or maybe how many pages do we have? 4 pages. If you're patient with me, I could do 4 pages. So that was 1. We still have more people. Okay. Hang on a second. That's 2. This is mostly nobody. And the last one is nobody. So there are 2 pages with the cameras on. Thank you so much. You all look very handsome and excited about LSST Cadence. So did I see some more questions coming in? Leanne has nice hoodie. It's with the old logo. You notice new logo for Rubin Observatory. So, okay, so it doesn't look like there are more questions. So let me reiterate that we are very excited about the interest you all showed. We had over 100 people. Let me reiterate that SCOC wants to keep this process very inclusive, very transparent, and that we want to quantitatively optimize the survey strategy so that we can extract maximum possible amount of science from the system and from the survey. There were good comments about synergies with other major projects, and we will rely on all of you who are also in other projects to help us better coordinate. And if you see that something is falling through the cracks and we are not doing something we should be doing to maximize science across the different projects, then please do step forward. There is always email you can shoot to me, to Michael. You can always ask for more technical information from me. If there are complaints, you can always complain to Michael. His committee is supposed to be community representative. and advice project on everything we do. So let's do it together. And if we all do it together, it will be the best of all worlds. So we'll have second workshop sometime later next calendar year. We are looking forward to your Cadence notes. Again, we provided those 7 questions to help you write your Cadence notes. But if you have an idea about something else that you think should be communicated to us, then of course you don't have to follow that structure. You can write about anything else that you deem important. We will make them public. You send them by email to me, and then we'll organize them in some public website. So you don't want to say bad things about data management or Lee and Guy or whatever. You want to be, you want to write something that goes to a public website. And thank you again. And I hope you have great holiday season. That is, COVID problem will go away soon, and maybe second workshop will be in person. Who knows? We can always hope. Thanks a lot, guys.
Thanks to you as well. Bye-bye.
Thanks for all the workshop. It was
Bye.
Bye-bye.
Bye-bye. Hey, Lynn, where are you going?
There's my unmute. I'm moving to Victoria.
Oh, that's cool. I love. So are you working at University of Victoria, or are you just commuting?
No, I will still be working with LSST, but Alex got a transfer to Victoria, so.
That's cool. Good for her.
Yeah, I'm gonna miss all UW and all the Seattle, but it'll be good in Victoria too.
Okay. Well, at least you'll be close. And now I got somebody to visit in Victoria.
There you go. Yeah, you definitely should come up and visit. And honestly, like it's good, nice to still be working with the project. So that's makes me happy too.
Yeah, I think my favorite night at a telescope was the Dominion Astrophysical Observatory.
Yeah. And I might have an office up on the hill there, so like a little tiny office, probably a shared office, like in they have some rooms that used to be like for the computers, and probably something like that. But
oh, that's cool. Yeah, I went up there with Anna Larson a few years ago, and I took my bike up, and so I rode up from Victoria. Oh, it was fun.
I did that a few times.
Yeah.
You know, people go up that hill just for fun and exercise.
Yeah, yeah, I can see why.
Yeah.
All right.
There you go.
Thanks for everything the last 2 days. That was really good. You guys have done incredible work.
Thanks. It's been a lot, but I mean, this is what we've been working on for the last few years. So
I know, but you've been
hopefully it sounds good.
The stuff you guys have come up with. It's just really incredible.